of the things I spend a lot of time thinking about and trying to work with are what I broadly call parallel programming models, and wondering which models work best. And there's a whole subtopic in computer science of language design, and it's really challenging. It's and you look at and you ask yourself, how much does a programming model really reflect the hardware that's under it? How much of it really gives us performance and performance portability? How much of it's independent of the hardware, and how much is connected? And you usually would say, hey, a programming language like Fortran and C and C++ is a lot more abstract than, say, something like CUDA or OpenCL or an FPGA programming language. And that's sort of true, but before you get too sure of that, the original IBM mainframes did not have stacks, so they didn't support recursion. And the original Fortran didn't support subroutines. They just thought, hey, I've just got some equations, we'll just run through them. Subroutines were added pretty quickly, but you weren't allowed to do recursion. And it's a classic example of a programming language not having a feature because they didn't know how to support it in the hardware. And the closer you are to the hardware, the less likely you are to let someone stray off and write a program that runs really, really poorly on the hardware. Eventually, on IBM mainframes, we figured out how to fake stacks or to allow recursion, and recursion is allowed in Fortran these days. We got rid of the tape statements out of Fortran. There were actual commands in Fortran to handle tape drives, but not too many people use those anymore. So those languages, languages have always had a history of being somewhat coupled to the hardware. But even on if you look at C programming language, the plus operators and the minus, those are because the Western Digital chips that were developed with AT&T had those built into the instruction set, and they wanted to make sure that the compiler used them. And the original templates in the compiler would match and use them efficiently. But to kind of goose it, they gave it the programmer that plus or minus symbol to try to use a feature they had in their hardware that was, at that time, I think it was unique to their hardware, but it was one of their addressing modes. You could use an address and then post or pre-increment it or decrement it. So they put it into the language. So it's a fuzzy line. So I'll share some thoughts on this and hopefully give some idea of how we've been thinking about this. But I would encourage, as much as possible, that we pay attention to using abstractions. And this is a hard thing, because how do you write a program that will give you performance and performance portability on as wide a variety of hardware as possible? If you program in something too specific to the hardware, you're giving up something. Do you gain enough in return? That's yours to decide. But the challenge is, what abstractions can we get? And I should define, so performance is pretty easy. Everybody in HPC knows performance just means you want your program to go faster, process more data, get done quicker, whatever. Performance portability is a more recent topic, and I don't think it's been discussed enough in the industry yet. The way I define performance portability is, if I tune my application to run reasonably well on hardware A, how likely is it that if I take it over to hardware B and recompile it and run it there, that it'll get reasonable performance there? So let's say I'm getting 70% of peak or 80% of peak on one machine. If I go on another machine and only get 20% of peak, that's probably not performance portability. Now, is 60% close enough, or 50? Can I tune from there? I think a lot of it depends on how much work is it to get up to an acceptable level. So if 65% of peak is reasonable for your application, and you get that on one machine, but you only get 50 on another, If it only takes you another day or two to figure out how to tweak the command line and a few other parameters to get up to the 65 that you want on the other machine, that's probably close enough to be called performance portability. But if you've written it in such a way that you need to completely rewrite it, that's a different issue. But do you need performance portability? I think we do in a broad scheme, but if theoretically your program only has 4 or 5 kernels that matter, maybe you're willing to rewrite them to specialty hardware. Maybe you're willing to rewrite them in CUDA for NVIDIA, or use OpenCL and have a different kernel layout for each one. Intel is a big supporter of OpenCL, and we see it really used well on our GPUs. But one of the biggest headaches I have with OpenCL users, and by the way, OpenCL is not popular in HPC, and I actually hope it never is, but that's not an official Intel position. That's an extreme bias on my part, and again, something that Tim Madsen, who teaches OpenCL classes with Simon McIntosh Smith, they teach these classes at supercomputing, and I constantly tell them I'm personally not in favor of OpenCL, but I'm actually in favor of whatever our customers decide to do. And the reason that, the thing that really gets me about OpenCL is that people will write a kernel, a beautiful kernel in it, and get great performance on some GPU, maybe an Intel GPU or maybe an AMD GPU. If it's NVIDIA, it's going to be written in CUDA, but that's why I didn't mention NVIDIA. But they get this performance, and then they say, hey, when I recompiled it for Xeon Phi, it ran terrible. I said, no kidding. Your code's mapping things into texture memory. It's doing this, it's doing that. You're writing it to an architecture. And there's actually, in the book that just came out this week, there's a couple of chapters on OpenCL. One of them is by ZIB in Germany, and they took a program and they wrote the kernels for a GPU, and they ran terrible on Xeon Phi. But then they rewrote them for Xeon Phi, and they ran great on Xeon Phi. They ran terrible on the GPU. No performance portability. But if that's only 4 or 5 places in your program and you can carefully craft them and set them aside, is that good? Maybe. I think it's really hard to get the memory hierarchy worked out in today's machines, but maybe that'll be better in the future. But where we are today, this is the view according to James. You've got libraries. There's lots of libraries out there for FFT, for BLAS, for solvers. We're actually introducing a library that does some big data operations as well. There's lots of libraries. Look for libraries. If you can use people's libraries, especially if you can find standardized libraries, you're riding on the coattails of other people. So if they work well enough, go use them. I would not encourage you to try to write your own matrix multiply. Vendors have probably worked on that a little bit. You should just use theirs most of the time. So libraries should not be overlooked. And Intel has a number of libraries that we'll keep updating. So like our math kernel library, which has BLAS and so forth, every time we introduce something new, we update our libraries, so you don't have to. So you can avoid that tuning from machine to machine. You can get that with Intel with our BLAS, or NVIDIA and their cuBLAS. You've got AMD will do something, et cetera, and IBM, everyone. So you shouldn't be writing your own and then tuning it to all these machines, in my opinion. And then if you look at MPI, MPI is a very standard thing to code to. And I think the challenges there with MPI is to worry about scale, which has a lot to do with synchronization. And I'll show this afternoon, if I get that far, shining a flashlight on your MPI application and understanding what's going on in there. But I think you can use MPI in a pretty performance and performance portable manner if you pay attention to being generic enough. And then OpenMP and TBB, this is really about node level parallelism. And OpenMP in general is best on Fortran and C, and TBB is most popular on C++. They're trying to solve the same thing, be very generic parallelism, let you express the parallelism, and then they map it on the hardware. And I still have Silk Plus on my slide, and I should say something about this. You will probably never use Silk Plus, and that's okay. Silk Plus is really interesting in that it asks the question, if we took TBB and put it into a language, what would it look like? And there's a fierce debate in the C and C++ committees about whether this is even a good idea. Honestly, we're not even sure at Intel. But it's a good debate to have, because if we can put things like this into the languages, it further standardizes, it further gets cross-platform support, and it's something to look at. But Silk Plus, it's had a number of great innovations, including one of them that I'll show you, the SIMD pragmas, actually is part of OpenMP now. This is the thing, this will be the curse of Silk Plus. Anything that becomes really popular will get absorbed into some other standard. That's what it's really there for, not to get people to use it directly forever. It's more about proving out something that might get into the future standards. Very exciting area. I encourage you to participate in it if that thrills you, but you shouldn't look at Silk Plus as something that Intel or I am endorsing as the future all by itself. But you can compare this with other proprietary, more proprietary or closer to the metal, NVIDIA CUDA or NVIDIA OpenACC or Intel's Leo offload directives. There are alternatives to these. OpenCL works to be an alternative that's more cross-platform. I say cross-GPU, but OpenCL says that it can go further than just GPUs. And then OpenMP has offload directives in it now that try to span the differences between these more close to the metal proprietary standards that we've seen. So I would discourage lots of programming in these methods. You know, why do I discourage it? Because I think that if you can find an alternative that works for you that's more cross-platform, more abstract, you should use it. But let's be real. If you've got a machine that depends on NVIDIA GPUs and you're not using CUDA, you're going to be giving up performance today. Now, I'm not going to stand here and tell you that that should be the future. That is the way it is today. They've done a good job with it, so let's go with it. If you go back a little bit and you look at offload to the early Xeon Phis, the best way to do offload to Intel Xeon Phis coprocessors was our Leo, our language extensions for offload, a very non-standard offload. NVIDIA's got an OpenACC, also not standard. Now we have OpenMP. So there's some hope going forward that the OpenMP target directive solve this problem for the industry and give us a cross-platform. That's what we should always be reaching for. But you know, don't let that distort the fact. You shouldn't be writing for tomorrow's machines today if it gives up huge amounts of performance. That's just not the way HPC is either. But it's always good to look forward and see, are we going to be able to bring these together and find a cross-platform solution that allows us to go across multiple machines. And I think we will in a lot of cases. And there's still a lot of holes. Doing a little bit of grading here, I'm still deeply disturbed that OpenMP is not composable. I just need to get over it. It's never going to be fully composable. Now, composable. What does composable mean? I'd like to be completely ignorant of what method of parallelism parts of my program are using when I write other parts. If you can do that, you're fully composable. The problem with OpenMP is that it's not. If you write a subroutine that uses OpenMP and then you have a main program using OpenMP and you call it, there's a relationship that happens there that isn't always, it's not always obvious what to do. And I'll speak to that a little bit more in detail here. And that's fundamentally because in 1997 when we created OpenMP, we just we underestimated the importance of nested parallelism. And the only reason nested parallelism's really gotten more important today is because the nodes and the machines have gotten fatter and fatter. If we would just kept them simple and keep it just a few thousand compute units per machine, you wouldn't need all this additional parallelism being exposed by us. But when we want us as programmers to expose more parallelism, we really like the abstractions to be able to handle that. So I'll speak to TBB a little bit. So this is a a project near and dear to my heart. I actually joined the team after TBB was mostly done. When I found out about it, I thought, oh my goodness, I can't believe we're actually smart enough to go do this. We asked the question, how should C++ be extended for parallelism? And it turns out C++ had a lot of gaps. And it's my hope that eventually C++ adds these things to the standard and the need for TBB is greatly diminished or goes away. And actually C++ 11 did some of this. They started adding things like portable atomics and locks and some other things. And hopefully the C++ 17 and 21 standards or whatever the numbers will end up being, we'll keep taking steps forward. But TBB is extremely popular. It's an open source project from Intel. It's by far the most popular way to do abstract parallelism. I said abstract. That's an alternative to P threads or Windows threads. There's still a lot of people that program the threads directly, but if we talk about C++ programmers, TBB is by far the most popular abstraction. There isn't even a close second. Now, when I say C++, I mean C++. I'm a C programmer that knows some C++. I don't write C++ programs personally. The whole idea of templates and generic programming and so forth, I can talk about them, I understand them, I can use them a little, but people who write C++ programs that really love generic programming and templates and all of that, they write beautiful code, and things like OpenMP just don't hold up for them for a variety of reasons. So this has helped drive TBB's popularity. And I said that TBB tried to plug all the holes in C++ for parallelism. Keep in mind, no programming language that's popular today was designed for parallel programming. C, Fortran, C++, Java, none of them had parallel programming in mind, not the type of parallel programming we do in HPC, where we're trying to get performance. The idea of concurrency is somewhat acknowledged in Java, underlying when it was announced. But it was really about concurrency, not about high-performance computing. And high-performance computing is tough. At a high level, the things you think of first for parallel programming is algorithms. How do I get a parallel for? How do I do a pipeline? How do I do a parallel sort? That's what the things in the upper left are, generic algorithms and flow graph features. Underneath it is a task scheduler. It's an open source project. We expose the task scheduler. You can call it directly. Some of our customers do. TBB is a class of abstractions that do what we call task stealing. And this comes out of the Silk research in the mid-90s from MIT. It's a pretty simple concept. Task stealing is really cool. Imagine we as programmers come up with a lot of parallelism to do. And we write down on a piece of paper all the tasks we want done. It's kind of like a job jar. And we go, let's put them nice and orderly up here in a pile. And then I want everyone here to help. So everybody rushes up to take a slip of paper. The problem is the task queue becomes a bottleneck. And so the simple concept that the folks with the Silk project came up with is distributed queues of work. And the idea is that every single node in the system, in TBB it's generally every thread, has its own queue. But when you run out of work, you steal from other people's queues so that you keep busy. The theory being, if I run out of work, I'm inefficient, I should steal work from someone else. And so I go sneaking around looking at other queues. And of course, as the work gets done, it's harder and harder for me to find work, but that's okay because we're running out of work. But in the thick of doing the algorithm, the likelihood that I will collide with someone else looking in a queue is very low. And it's very scalable. And that's what task stealing is about. Task stealing is strictly about trying to load balance, but without a central queue, because the central queue becomes a bottleneck and kills you on scalability. And it gets really complicated beyond that about all the different things that go on. But TBB implements a very sophisticated task stealing method that tries to be aware of caches and things like that, tries to give you good performance. Now, one of the things if you've got a program that runs pretty close to synchronous, and a lot of OpenMP programs have been like this traditionally, they'll do a static decomposition. A static decomposition simply means if I've got 1,000,000 things to do and I'm running on 10 cores, I'll give each one 100,000 things to do and I'm done. I don't come back to load balance. TBB never does that. TBB is more likely to give each one of them 10,000 things to do, and then when they get run out of work, let them do 10,000 more. Actually, what it'll do is it'll give each one of them 100,000 to do, each of the 10 cores, so that the 1,000,000 gets done, but none of them will actually start doing 100,000. They'll actually peel off 10 at a time, and if someone comes in to steal, they'll steal half the work, not all of it. That's how it works in TBB. It's a load balance. But if it turns out your machine's really synchronous, the static decomposition in OpenMP will be faster because you have none of this overhead. People will look at TBB and say, this overhead's horrible. It's only horrible if you have a perfectly decomposed program that doesn't have this. And remember I said that the thing that struck me about the talk last year that showed that Sandy Bridge machines were running at different speeds because of thermal, you also get things like OS processes coming in and giving you jitter. The bigger your machine is, the more likely dynamic load balancing will help you a little bit anyways. Other things we did, the standard lib. Standard libraries for C++ are not thread safe, so we fixed some of that. We provided some alternative highly concurrent solutions for things like queues, synchronization primitives, portable things. Hopefully the C++ standard is going to make this less and less required, but the atomics, we still have some atomics and synchronization capabilities that are very portable. Thread local storage, miscellaneous things. Oh, and the one on the bottom I shouldn't ignore, a thread-aware memory allocator.
Yeah, sorry. Does TBB work like OpenMP, like mainly through compiler directives, or is it like there are classes,
Great.
C++ classes that are like vectors and array, they're inherently parallelizable?
Great question. So is it working through directives or not? So OpenMP requires a compiler that knows OpenMP because it's built into the language essentially as directives. TBB is a template library, completely independent of the compilers. A little thing about Silk Plus. Silk Plus tries to reunite them because some of us, sometimes the fact that the compiler doesn't know you're doing parallelism, some of us think you could do a little better if the compiler knew what was going on. In practice, that we haven't been able to prove that. It works pretty well. And that's part of why TBB became so popular. It's an open source template library that's easy to port. There's even some of the folks at Argonne did a Blue Gene port. I don't think it was ever used a huge amount in production, so I don't want to overstate it. But it has been used extensively on many, many architectures and OSs because it's so easy to port. I mean, you don't require a different compiler for it. Its real magic is in the task scheduler and the memory allocator. The memory allocator is completely orthogonal to TBB. Remember I said we wanted to fix C++ for parallelism? Well, it turns out when you keep your eyes wide open and try to figure out why your parallel program's not running fast, memory allocation can be one of the reasons. If you're allocating memory, using it, and then giving it back to the pool, and then allocating memory again, and so on, the things that can happen are mind-boggling. You can get false sharing because I gave you an allocation and someone else an allocation, and they share a cache line. So we don't do that. The other thing, though, is you might be using the memory, and you give it back to the pool, and when you request other memory, who knows? There have been calls in and stuff. By the way, mallocs tend to have a global lock, which is another problem. So we don't have that with this memory allocator. But the other problem is I'm running on core 0, and I've been using this memory. I give it back, and when I'm given more memory, when I ask for the next malloc or do a new in C++, I might be given memory that was most recently used by core number 2. And that probably means the data associated with that is in core number 2's cache. And so you start getting cache issues. And so TBB's memory allocator does pooling, which means it highly biases if you do a free and you do a malloc, it highly biases to try to have that memory and give it back to you because you were the last one to use it. So it's still probably in your cache, and it biases, and it only very reluctantly will give memory to a different core than was using it previously. I quite often see it give 10 or 20% performance. And every time I give this talk and plug that, I will say, but I've had people tell me I understate it. One time I was doing a talk at Cambridge, and someone stood up in the talk and said, we got 400, or we got 400%. They have 4x in their program. He said I was understating it, and I said, well, that sounds pretty dramatic. But what was happening with their application is they were doing a lot of small mallocs, and they were doing a lot of news and deletes, and they were being thrashed in a multi-core situation. And they did. They got 4x in their application switching to TBB malloc. I have a mail in my inbox from a month ago. I did a talk, and someone sent me another example like that. It's really cool, where it really changed the performance. So, one of the things when we talk about performance tuning is you really need to figure out what's going on the machine. And if you could actually see the thrash that memory allocation and deallocation can cause, you should pay attention to it. So if you have an application that's doing a lot of memory allocation and deallocation, and you're not using a thread-aware memory allocator like TBB's malloc memory allocator, you should be. It's low-hanging fruit. Anyways, that's something we added to TBB. But we've got lots of generic algorithms. This was kind of interesting. So we put a lot of things in TBB. We did parallel invoke, which is a parallel function invoker. Invoke these functions in parallel. We did a parallel sort. We did a parallel, we did some flow graphs more recent, parallel do's and whiles and scans. Scans are very cool. Not everybody knows about what a scan is. And you've got parallel fors and reduce. Microsoft actually imitated TBB. They called it TPL and PPL in their C++ and .NET. And I worked with a team up in Microsoft for a long time and tried to convince them to just use TBB. They said they needed to simplify it. And the way they simplified is they only implemented parallel for. And this caused a lot of debate. Should we really have put all these functions in, or should we have just given you a parallel for? Because it's kind of like a Turing machine. You can do anything with a parallel for. In fact, the parallel sort is actually implemented using parallel for, but we expose it as parallel sort. We've just cleverly written it. You could write anything with a parallel for. And so we had that debate. The jury's in. TBB's 10 years old next year, and I can tell you that users much prefer having all these interfaces. Their answer is, I don't really want to program a Turing machine. If I can get a parallel sort and call it, I want to call it. I don't want to write one myself. So I think that worked well for us and made TBB more popular. I'll just take a peek at parallel for, because this is a template library. So I want to show you what it looks like. And the good news is with Lambda functions, which are new to C++ 11, it looks a lot better than it used to. But parallel for essentially looks like this. We used to only support the bottom one, parallel for, range, and functor. That's a little strange. These two interfaces were invented by Microsoft, and we worked with them closely, and they said that they really wanted an easier thing. They wanted the parallel for to have a lower bound and upper bound and the body that you want to execute. Look more like a for. We had range because range has to do with divisibility. When you're doing task stealing, a range says here's a block of work, and then a range can be subdivided. The parallel fors with uppers and lowers, that's only a two-dimensional range, or it's a one-dimensional range, and it can only be divided one way. TBB is more sophisticated. You can have two-dimensional and three-dimensional ranges as well. But anyways, you can have the simple one-dimensional case, and you can write a program that looks something like this. And the key things here is I've got a function. There's nothing mysterious in this function other than it's a dumb little function to compute a prime. But here's parallel for. Go from 0 less than n, a stride of 1, and then this is the invocation of, it's a functor that calls prime, and it's, if you like C++, this doesn't look too ugly. If you're not a C++ programmer, you're probably horrified. I can only tell you it looked a lot worse when we had to do class member functions before lambdas came along. It's not hard to learn. This is what TBB tends to look like when people write code. They go to a section of code that used to be a for statement and they turn it into a parallel for. Now, we could make that a keyword, but that would require a change to the compiler, hence the debate. And some people on the C++ language committee say if you can do it with a library or a template library, you should not corrupt the language. And that's why TBB is what it is. And I don't think the standards committee is likely to add parallel for to the language. But I might be surprised because they seem to think it works pretty well as a template library. And the last thing to say about TBB is it does understand when it does task stealing. You know, I told you might give it 100,000 things to do. It will keep breaking it down and only do a small chunk because it always wants to keep a lot of work available to be stolen from it. And of course, it'll keep going back to its queue and using it. It's smart enough, though, as it divides things in half and takes half of it and sticks half on the queue. And if this is still bigger than it wants to do, it divides it again. It keeps putting stuff on the queue. When work is stolen, it's stolen off the things that were put on the queue the longest ago. And I've got them, I guess this is kind of blue. I'm partially colorblind, but I think it's supposed to be blue. The things that are cold. So the task stealing tries to steal work that's cold. And that's all just kind of built into TBB automatically, but it's good to know TBB is, the task stealing tries to be cache sensitive because you can't completely ignore the machine. So now TBB is very popular for C++. So in the interest of teaching properly, you know, it's really good. You should just give up on OpenMP. It's trash. OpenMP just doesn't work. Forget it. And let me prove it to you. There's a benchmark called Stack A2. Yeah, you see where it might be going. This is it's a benchmark that does, it's a financial markets risk analysis benchmark. And here is a side-by-side, very fair comparison of OpenMP to TBB. And it pretty clearly shows that OpenMP sucks. We get much better performance using TBB, so I don't even know why we would have OpenMP ever. So, you know, yes, I am one of the keynotes for the OpenMP conference coming up in September. I really haven't given up. I'll tell you where these slides came from. I did a class, Martin Watt, who's at DreamWorks, is teaching a parallel programming class down at Cal Poly this summer. And he asked me if I'd come teach TBB for a few days. He spent the first week on OpenMP. And so I show up. I didn't tell Martin. Martin's sitting in the back of the room, and I did this, but with a much straighter face than I did here, because no one chuckled. This class of about 30 students, their eyes kept getting bigger and bigger. And I actually said, I don't even know why Martin wasted the entire week of class last week talking about OpenMP. And their eyes get bigger and bigger. And Martin's sitting in the back of the room starting to laugh, but none of the students are looking at him. And then when I say, look, let's take a look at this, I can tell you what happened here. OpenMP works pretty well when you don't need the dynamic nature of TBB. When you control the entire machine, when you only need one level of parallelism, and when you want to take control, statically decompose or whatever, OpenMP does really well. But TBB, if you start being dynamic, you start having virus checkers run, you start having a machine that's not as HPC-like, or if you need lots of levels of parallelism, TBB can really kick OpenMP's butt. And I went through this, and then I warned the class, I'll warn you, don't ever let anyone tell you that one programming model is vastly superior to another. It's unlikely. If you put enough effort into anything, you can probably make it work well. The question is how much effort. And TBB is much easier when dynamic parallelism and multiple nesting is necessary, but when it's not, OpenMP does really well.
Oh, you might have just answered that. TBB is only for C++, so if I use Fortran, I'm going to use OpenMP. So.
Yeah, the question is TBB only for C++? Yes, absolutely. It's a template library, which is a feature of C++. Yes, I know. When I speak C++ to explain C++, it doesn't help Fortran programmers know what I said. Templates is a feature that's only in C++. I actually went to OSCON, which is mostly, it's an open source conference, mostly a C conference, and I tried to sell TBB. In fact, I launched it there, and I learned I should quit trying to even sell it to C programmers, but I've never even tried selling it to Fortran programmers, so that would fail really badly. It's very much about C++. Some of the concepts have gone back and helped OpenMP a little bit. So anyways, I was having a little bit of fun, but it's like, I love going to conferences where someone will get up and talk about a programming model and tell you why it devastates all the other models. And they show graphs to prove it, just like my TBB graphs prove that OpenMP sucks. And it's like, I can just sit there the whole time thinking, what aren't they telling me? Because I just know that programming models can change ease of use, but in general don't have an effect on what you can do, because a Turing machine can do anything, right? Anyways, nested parallelism is getting more and more important. So let me talk a little bit about OpenMP's runtime model. OpenMP, if you're running on a quad core, I'll just keep it simple with small numbers and not talk about million core machines, but it's there aren't any million core shared memory nodes that I know of yet, so I'm okay. Four cores. What OpenMP will do is it'll have 4 workers that work on your program when you're in a parallel region. And when you're not, only one of them is doing anything. Well, getting a thread from the operating system, a thread of execution, which is something the OS will schedule. You have to talk to the operating system. You may have to go through different privilege checks and things like that. But the operating system has to do a bunch of things on your behalf, and it's kind of expensive to get a thread. So you create threads. So everybody that's implemented OpenMP is smart enough to have realized I should create my worker pool once. And even if I leave a parallel region, I'll keep them. I'm not going to give them back to the OS and then go through that overhead again. So every OpenMP implementation does this. I run on a quad core. The first time I need a parallel region, if not earlier, I create 4 worker threads, and I keep them, even if I come in and out of parallelism. And so that helps a lot. Now, one of the problems with OpenMP is it doesn't maintain a central work queue or even an illusion of one like TBB. It decomposes the program in the parallel regions and maps them out. And so suddenly you've got 4 worker threads. If any one of those worker threads has additional parallelism, say they call the MKL library, but they have parallelism turned on, and MKL says, hi, oh, I'm running on quad core. Voomp, let's create 4 more threads. Well, each one of these guys can create 4 more threads. Well, this is one of the problems with OpenMP. If you do that multiple levels of nesting, you'll just blow out your memory. You'll run out of stack space. All sorts of horrible things will happen. It's not very efficient. So most implementations turn off nesting in OpenMP. The first time you hit a parallel region, you get parallelism. If you add more parallel regions, nothing happens, because they don't want this to happen. But we need this to happen. But there's another dirty little secret. All the implementations out there, when you create this next level of parallelism, when you exit it, it gives it back to the OS. Because the implementations have kind of assumed this is an aberration. You don't want nested parallelism in OpenMP. And that's the way we've done it at Intel as well. And so that overhead actually guarantees pretty much that OpenMP nesting is going to be low performance and suck. Just that thing. The whole idea of blowing out memory and explosions and stuff is a problem. So now I said I worked on this book that just came out. I actually have not seen a copy of the book yet, There might be one in my desk when I get home, or within the next week I might actually get to touch one. I've read it 20 times by now. But there are two chapters in this that use nested parallelism very, very effectively, chapters 10 and chapters 18. Chapters 18, Zhang Nim, she was at Oak Ridge until a year ago or so. She's really excited, talks about nested parallelism all the time. We have this thing called hot teams. I think this is going to happen. I think hopefully the OpenMP Standard Committee standardizes something like this. If they don't, everybody's going to implement something like this. I just think we're first. It's another environment variable that says, hey, Mr. OpenMP runtime, I want you to allow an additional level of parallelism. A lot of OpenMP libraries allow this. But then we have a hint that says we want you to keep them hot. Don't give them back to the OS every time I come in and out of this. Basically, do the same thing at level 2 that you did at level 1 of parallelism in OpenMP. The results are phenomenal. And the reason the results are phenomenal now and wouldn't have looked phenomenal 10 years ago is because we need this parallelism. We have enough cores on a node that the nested getting to get that more parallelism exposed actually matters. And so chapter 18's got some good examples. The folks at Cambridge Theoretical Physics Lab, this is Stephen Hawking land, the Cosmos work, they use it very, very effectively, nested parallelism in OpenMP as well. They use the hot teams as well. So it's sometimes, one thing about changes is you need to know the change is happening. So common wisdom in OpenMP is don't use nesting. And I'm telling you, if you hear that, question it. You probably are going to use nesting. You can't use infinite depths of nesting yet because we don't have that much memory on the machines, and we probably never will. But you want to open it up to an additional level. But ideally, you need to have the runtime for OpenMP not give those threads allocate and deallocate them over and over again. That'll kill you. So the hot teams capability in our implementation gets past that and seems to, for a lot of users, give that extra level of parallelism helps you use the machine better, and the hot teams capability to not be giving it back and forth actually makes the performance acceptable. So a cool feature to look for, and like I said, yeah, it's really cool we put it in first. It's a good idea. It belongs in all implementations, and I expect others will do something similar, and hopefully OpenMP committee will standardize it. The little thing, the KMP, if it says OMP on the environment variable, that means that's standard in the OpenMP standard. For Intel, KMP is our non-standard extensions to OpenMP. For extra bonus points, anybody know why it's KMP? Where the K came from? Because K is not exactly a letter in the word Intel. Nobody at all. There's a little company in Champaign-Urbana that we acquired more than 10 years ago, Cook & Associates. I shouldn't say little. A fantastic group. Cook & Associates was famous they were one of the co-founders of OpenMP and did a lot of software to help with vectorization on Cray machines and then many other machines. Cook, it stands for Cook, and we've never changed that. Little bit of history, and the team still actually is the one that does our OpenMP runtime. So let me switch up. So TBB and OpenMP help you scale. They're both solutions. OpenMP is a set of directives that gives hints to the compiler how to parallelize things. TBB is a way that lets you express parallelism in C++. So between the two of them, we've got Fortran, C, and C++ covered. And I would always say parallelize your program first. In fact, I worked with some folks down in Hollywood. This would be DreamWorks Animation, Pixar, and I had some co-authors. We taught a tutorial at SIGGRAPH a few years ago, and then we published a book based on it. And we're actually teaching the class next week. I got to work on those foils next. But we're teaching our tutorial next week again. And it's funny because you can read through the whole book, and most of the usage is TBB because it's a C++-centric world. This is not a HPC. But you'd be hard-pressed to find vectorization. Now, what's funny is we taught the tutorial in 2013. The one that we're teaching now, the number one thing that my co-authors are adding to their slides is vectorization. But I asked them, why did we do an entire tutorial and hardly even mention vectorization? And the answer was, well, parallelization is more important. And they're right. If you've got 16 cores, you could get 16x performance, but if you can only do 4 wide or 8 wide parallelism vectors, you only get 4 or 8x parallelism. So the math works out pretty well. It's getting a little blurrier now, but vectorization's the next thing to do. But for HPC, the reality is you really need to do both. I'll do a little simple math. Use a Xeon Phi. 16 wide parallelism if you use our vector instructions for single precision, but up to 244 way parallelism if you use all the hardware threads, which is 4 threads per core, 61 cores. So again, parallelism seems to offer more. Now, tongue-in-cheek a little, there's an urban legend that Einstein once said that the most powerful force in the universe is compound interest. So here's my example of compound interest. 16 vectorization can get you this tiny bit of performance. Parallelization can get you this 244. If you do both of them, back of the envelope, you can get 3,904x performance. Good luck, but it's there might be some factors that mitigate this, but the combination of them is multiplicative for obvious reasons. If you got every core also vectorizing, you get performance. So vectorization turns out to be incredibly important to take advantage of performance in computing devices. Now, GPUs don't tend to differentiate the two of these, and CPUs do. Kind of an interesting phenomenon. GPUs don't have the same independence between their threads as CPUs do, so they generally, the programming methods blur the two because there's not a benefit at differentiating between a thread and a vector. It's all about the same thing on a GPU. This would be Intel GPUs, NVIDIA, AMD, anyone's GPUs. That's fundamental to their design. But a CPU gives them enough treatment that's different that you will treat them differently. So that means that you can use OpenMP or TBB to get you your scaling, but then what are you going to do about vectorization? And so let me just quick poll. Let's see if you're awake. How many people have ever done something to try to get code to vectorize? All right. So applying a shyness factor, I'd say it might be more than half of you. It was less than half of you that raised your hands, but so I'll make an assertion, and then I'll explain what it's about. We really need to embrace what I call explicit vectorization. And this is a game changer, I think, in how we think about getting code to vectorize. And so I want to explain it a little more. Now, first of all, people ask me all the time, can't we just ignore vectorization? Won't tools do this automatically? Can't we just ignore it and hope the compiler does it? And the short answer is no. You need to do something about it in general. You need to at least be thinking about how to get your code to take advantage of these SIMD instructions. And the promise is pretty huge. And Intel's been investing a lot, and you'll see other vendors, the same thing. You know, we had SSE, which is 128 bits wide. AVX is 512 or 500 or 256, and then the AVX 512 is 512 bits wide. The 512 bits means you can do 16 single precisions or 8 double precision computations in one instruction. Presumably, the instruction runs at roughly the same speed as a normal math instruction. That's actually true on a Xeon Phi. On a Xeon, it's not quite true anymore. For complicated reasons. Usually on a Xeon, you'll get a little slowdown using the AVX. It won't quite be a linear speed up. But on Xeon Phi, it is. And so you can see all sorts of wonderful things that say speed ups. All right, that's kind of a marketing foil, so we'll skip it. What's a vector? What's vectorization? I want to make sure, again, that I don't leave the concept of vectorization as a fuzzy concept. When I say vector, because vector, you could get carried away and think I meant more than I do. This is a vector of numbers. I think it's 11 of them, if I remember, just to be goofy, because there's no machine that does 11 that I know of. But it's just a set of numbers. And a vector add is a item by item add. No dependency. This is what I mean by vectors, and this is what I mean by a vector add. Addition. So this first vector has a negative 0.3 in this spot. This next vector has a 0.1. When I do a vector add, I get a negative 1.2. It has nothing to do with any other column of numbers. And you can do multiplication this way. In fact, I think this is the one that trips people up. Start talking about vector multiply, some people think I'm going to end up with a matrix or something, and it's not. Or people worry about that. It's just pairwise. So we can start with an example program. Here's a nice little C program, right? Yes, C. And it looks nice and simple. And normally if I was a compiler, what I'm going to do to implement this loop is I'm going to load this data into a register, load this data in a register, add them, and then store them back. And so this is the sort of code that I would like to create. Oh, and then I increment my index by 1 and go through the loop again. That's actually what the language says I should do. And to vectorize, here's what I want to do. I want to load 4 things from A, 4 things from B, add 4 of them in parallel, store 4 of them back, and then increment my index by 4. Now this will cause, the compiler has to deal with all sorts of things like what if my loop's not divisible by 4, what if things aren't aligned properly, there's all sorts of problems here. But at the end of the day, this is what we call vectorization. If the compiler looks at that original program, which should have created this code, and it creates code that looks like this, that's what we call vectorization. All right, pop quiz. This loop's actually not legal to vectorize. All right, there's a hand up. Yes, why?
Because the pointers can overlap.
Yeah, the pointers can overlap. Very good. They could be aliased. One of the ugly things, these are just pointers to anywhere in memory. What if every time I write to the C array, I'm actually updating the next element in the A array? Then I have no business picking up 4 elements of A at a time because every time I update C, I'm going to update. So the vector version of this doesn't work the same. True story, in one of the operating systems about 10 years ago, I won't mention them, but it wasn't Linux. There was a part of the OS that used memcopy. They put one element in a place, and then they went in a loop just like this, doing a copy that was off by 1 byte. This is horrible. I mean, first of all, machines aren't even byte-oriented anymore, but the other one was, it meant you couldn't vectorize, you couldn't do anything to this loop. So the compiler has to be conservative. And so this brings in the question, okay, what's the big deal about making something vectorized? Well, you have to wrestle with the fact that the language wasn't designed for parallelism. It just wasn't. And so what are we going to do? Well, you could start by throwing a switch and saying, vectorize what you can, compiler. Well, it's not going to vectorize this loop because if it vectorizes it, and as our friend in the back pointed out, if you call the function with overwrapping arrays, it won't work right. Now, you could potentially create 2 versions. And when you start the loop, you could check to see if they overlap. Well, there's a couple problems with that. One is you've created 2 versions of the program. That takes up twice as much space. And if you lay that out in memory, you're going to have more iCache misses and more ITLB misses, and you're going to have performance issues. And the other thing is that little check takes time. And it may not seem like much to you, but if it's the innermost loop of a critical part of your HPC program and you inline it, and that check just kills you. So you don't want to do that. The other thing is you could start giving hints and hope that it vectorizes, because hints, all they do is kind of nudge the compiler closer. Well, The C99 standard, not C++, allows you to use this restrict keyword. By the way, all the C++ compilers I know of have a switch to allow this extension to C++ as well, even though the C++ Standard Committee hasn't gotten around to adding this yet. Restrict means, oh, I'm going to use 1956 technology. Fortran actually, in 1956, in their original spec said you're not allowed to alias parameters. That allowed all sorts of compiler optimizations. They knew that in 1956. We get to 1999 and C catches up. In Fortran, it's illegal to alias parameters. In C, if you say restrict, restrict has a really simple definition. When you say restrict C, it means I promise that all accesses by C, that there's no other way that that memory is going to get updated. Nobody else points to it and changes it. That if the compiler assumes that when it writes or reads something from C that it doesn't change in between by any mysterious circumstances, that's what restrict promises. Now, a more ancient way to do this is something called pragma IV depth. This is available in Fortran and C. It means ignore implied loop dependencies. And if that sounded like a foreign language, that's because you don't speak compilers. And I'm a compiler writer. It means tons to me, having read many, many dissertations on disambiguation. This is a beautiful thing. It's a terrible thing to try to teach. In fact, I can't even explain exactly what it does because it varies from compiler to compiler. But good luck. You could try it, and maybe it'll work. And it often does. But here's mandatory vectorization. And this is a feature of OpenMP now. Pragma, OpenMP, SIMD. And it says, vectorize this loop. Now, keep in mind, I might call it with arrays that are too close to each other. So this pragma changes the behavior of the program. But it conveys an intent from me as a programmer. It says, look, I want this thing vectorized. I understand the implications, just vectorize it. And I thought this was the dumbest idea I ever saw in my life, honestly. The first time I saw it, put in Silk Plus, I argued with the engineers. I was wrong because it turns out what I didn't like about it was when you use this, it might break your program. And I thought, oh, our job is to keep everyone safe. Now, when we keep them safe, we drive them nuts because you can't figure out what additional thing you need to tell the compiler to calm it down and get it to vectorize. This, it'll vectorize. Now, if you goofed and vectorizing wasn't a good idea, like there was overlap or dependencies, you'll get a different answer and you get to debug that. We're not going to save you from it. This has been very popular. And it's what I call explicit vectorization. So anyways, encourage you to take a look at that. I'm going to flip through the...
What's it do for procedure calls?
Oh, so so there is a procedure call equivalent. I'll go back to that. I meant to stop. You can do declare this. If CUDA means anything to you, this basically creates a CUDA kernel, sort of. And by that I mean this function was intended to operate on one float at a time, to add two floats and create a result. Well, you can see that that's not too efficient in a machine that can do vectors. So this declaration here says, I want you to create vector versions of this. So if we're on an AVX machine, AVX 512 machine, the compiler will automatically create a version of this that's 16 wide. And when it's called, if at all possible, the compiler will try to call the vector version of it. So you might be in a for loop, and you would call it to operate on 16 things at a time. It's actually, the compiler can do lots more than I just said. It can produce many versions of this and call the right version depending on the machine you're running on, et cetera, et cetera. The ultimate thing is if this gets inlined. So you've told it that you want to vectorize this code, and it gets inlined. That gets you the most performance. But sometimes you have functions that are pretty sophisticated that could benefit from having them have wide interfaces instead of just be scalar. Now, I could rewrite this code to operate on 16 at a time, but that would be an example of me as a programmer writing to the hardware. I'd really like to keep writing programs like this and just augment it and say, hey, compiler, vectorize this on whatever machine it is today. Because who knows what Intel's going to do to me in the future. They're probably going to come up with an AVX 1024 someday, and I don't want to rewrite my code again. That was not a product announcement either.
Just this assumption is nice, but many algorithms depend on the width. Say we have a voxel that is of size 4. Then if SIMD width is 8, then I need 2. If SIMD width is 16 in that precision, then I need more. So
Yeah.
how do I express that?
I make things look really pretty if I go fast enough. Yeah, and there are, the OpenMP committee discussed a lot of those things. There are additional things you can put on the line about what a safe width is and a bunch of things. You have a lot of controls. And then I'm not going to say that they've accommodated everything. In your particular case, you may have to change your code or parameterize it a little bit to get the effect you want. This goes a long ways. We're getting experience with it. If you've got ideas or code that this doesn't quite go far enough for, I can promise you we're very interested. The OpenMP committee is very interested. So I like this explicit vectorization. It makes it our problem as programmers to get it right, but we can quit fighting with the compiler. And I really underestimated how much hatred there was for fighting with the compiler, partially because I can read the compiler output messages and understand what it's complaining about and realize how to undo it given enough time. This is actually faster, even though I can do that. So it's definitely a better idea. So that said, I just want to hit a few things. So look at the standard a little bit. So let's see. The SIMD construct is pretty simple. But there's a few other things that are interesting to think about. This is part of the OpenMP standard. There's one of the things you can do is that my next slide? You can do a parallel SIMD 4, and this is an interesting thing. So in OpenMP, you can do an OpenMP 4 to get parallelism across cores, right, or hardware threads. And then I just said you can get SIMD and get vectorization. But usually what you do is you do a parallel 4 on your outermost loop to get parallelism, and you do your SIMD on your innermost loop. But what if they're the same loop? What you would like is the compiler to distribute across all the cores and then vectorize what runs on each core. And that's what OpenMP 4 SIMD is. It says, hey, I think this loop should be vectorized, but I also want you to split it up. I don't want you to necessarily just run it on one core. So those ideas can be combined. Now that becomes more powerful when we look at a little bitty thing down here called collapse. One of my favorite little features of OpenMP. Collapse, and you can specify how many levels, but if you say collapse 2, it takes the next 2 loops and collapses them into one. Now, people in the past would call that loop unrolling. But you don't have to change your code to get it. You just say collapse. And by the way we used to do loop unrolling is you'd rewrite the code and probably debug it if it wasn't simple, and then you'd run it and see whether it ran faster. With collapse, you can do the same thing by saying collapse 2, compile and rerun it and see if unrolling gave you benefits. Now, the reason it might not is it might increase the size of the instructions, and that might have adverse effects. But in general, it probably give you some speed up, or at least be the same. If it's the same, you probably shouldn't do it because you're increasing your size of your program. But the collapse is really cool because the collapse means you don't need to unroll your code. Again, the objective of OpenMP is to put some hints to the compiler that let it do the things you wanted to do to your code without making you change your code. And then you can put if-defs around, and maybe you want to use one pragma on one architecture, one on another, but at least your code stays the same. Hopefully your code looks like your science, and the directives are what bridges the gap to mapping it to the hardware. Again, the reason we need these directives is because the language wasn't designed for parallelism. What we're doing is putting a Band-Aid on. Pretty good Band-Aid, but. So the collapse directive is really, really powerful. And if you combine the collapse with the OpenMP 4 and the OpenMP SIMD, you can do essentially an unroll, a vectorization and parallelization of a loop nest, all with some directives, and leave your code looking like the original science. So I encourage you to take a look at that and give that a try. There's all sorts of good vectorization reports in the compiler. We've invested a lot. The compiler can tell you why something vectorizes or doesn't, give you advice. And then we have a tool that's brand new called Vector Advisor that can suck up this advice and look at it and such and give you some feedback. This is a very new tool, just this year. So if you're using the Intel tool set, I'd encourage you to take a look at it. I highlight it because it's a new capability, so you may not have seen it. It's a tool that tries to give advice about vectorization based on what the compiler knows, the messages it's spitting out, looking at your code, all of that stuff. It may or may not help you, and it'll give you hints where to put pragma SIMDs and things like that. So that's, yes?
Do your people have to buy that, or is it included in some Intel suite of things?
So the Vector Advisor is included in our larger suites, like the Parallel Studio or the Parallel Studio for Cluster Edition. So I think if you're using the Intel tools, probably a good chance this is just part of the 2016 suite that you probably have. Yeah, most people buy the suites, and it's not a new product in that respect. It's part of the suites that most people use. It's a feature of Parallel Advisor. So it's a vectorization advisor inside Parallel Advisor, which is part of Parallel Studio.
And universities get a pretty good deal on that, right?
Yes, and academic researchers can get it for free with our academic researcher program. Yes. So that was a whirlwind tour of a bunch of things to know about. And by the way, I don't usually carry business cards. I'm not very good at that. But my email, be patient if you send me email. I might not respond right away. And if I don't, and you think I'm ignoring you, send me another email and say, what the heck, a few weeks later. But I love to hear from people, too, if you've got questions after today. I'm going to be around most of today. I'm flying home tonight, though. Unfortunately, I've got to be in a meeting tomorrow morning back in the factory. But are there any questions about this material or anything else?
Yeah, you talked about nested parallelism of like OpenMP threads. I was just wondering if you had any thoughts on nested parallelism as in like, an MPI program over a distributed machine, then with nested OpenMP or TBB or whatever within each node.
Now, I'll repeat the question in a moment, but you're asking about nested. Are you just thinking about nesting on the node level, or are you talking at a higher?
Yeah, nesting on the node with like OpenMP or TBB or whatever, but within an MPI program over a distributed architecture.
Yeah, so the question is, I talked a little about nested parallelism, and you were asking me about what about nested parallelism at the node level. Absolutely yes. One of the scourges of HPC is static decomposition, and it's just one of the things that I guess everyone in this room, as you work on parallel programming, you're eventually probably going to undo static decomposition because machines just aren't that way. So you can have an MPI application, and it can have individual nodes doing work. And absolutely, each one of those nodes could do nested parallelism, OpenMP or TBB. But I'll tell you what, when you start using nested parallelism, the reason probably is because you have workloads that have a lot of variety to them. In fact, in the early days of OpenMP, the reason we didn't worry about nested parallelism is everybody knew all the computation was done in a nested loop that you could see everything in. But parallelism's gotten a lot more complex than that. I've got amazing things that people ask to be vectorized or parallelized that include function calls and table lookups and all these things. And a lot of the science we're doing now demands that, or you're doing things with graphs and whatnot. And so nested parallelism often arises when you find work to do and it's enough to invoke more parallelism on it. And you do that at the node level, and it works beautifully. The problem in an MPI application is that's probably a symptom that your nodes may not all be doing the same amount of work. And there's a lot of simulations out there, like in-body problems, where you start off with distributing the data real evenly, and after you step enough, for some reason, molecules attract and stuff, and the next thing you know, one node's doing more work than the others, and you're not balanced anymore. So I think the elephant in the room is, how do you do load balancing across MPI? And my personal belief is that remains very much an application job to do. And as you think about your algorithms and decomposing them, I would warn you that if you do a static decomposition or one that's permanent, you're probably making a mistake. Keeping a machine balanced needs to you need to have some concepts how to do that. So yeah, there's actually, I got to see a little bit of this in the two books that I was talking about. The books, I call them Pearls books. They're called High Performance Parallelism Pearls. You might notice parallelism and pearls is an alliteration. It's kind of like GPU gems, but it's not a G, it's a P. But parallelism pearls, so the Pearls book, I call them Pearls 1 and Pearls 2. There's at least a couple of chapters doing work balancing over MPI, and they're doing it at a program level. But they are trying to solve problems like in-body problems that get out of balance, right? And if you really look at a machine, if you do a static decomposition, but your data isn't even, and things like in-bodies where molecules are moving around and next thing you know, they move to another node, some nodes get more work to do. So it's a long-winded way of saying if you're doing nested parallelism on the node, there's a good chance you're going to need to worry about load balancing at MPI at some point to keep the machine busy, would be my guess. That would be my immediate worry if I heard you were doing nested parallelism. But start with the nested parallelism on the node at least. Make good use out of the node.
Other questions? There's one in the back.
I have a few, but I'll restrict it if I have to. One of the main questions is OpenCL is missing from your slides.
Actually, I had it there. I thought I said bad things about it, but yes, go ahead.
Missing in crucial points where we're talking about especially portability and especially at the part where you crossed out OpenACC, CUDA, and the third, what was the third thing?
Right.
And I was expecting that when you crossed it out, then OpenCL will pop up, but it didn't.
All right, so the question is, what about OpenCL? Well, actually, in the slide you're talking about, if it was CUDA, OpenACC, and Intel Leo, which are these last two are offload. And then I said there's a generic alternative, and it was OpenCL for CUDA, and then OpenMP. But you're right, OpenCL never appeared in a nice light on my slides. And that's because this is an HPC audience. Like I said, I don't think OpenCL is a good idea for HPC. Now, let me explain. OpenCL has gotten really good results on Intel GPUs. In fact, it's probably the best way to program an Intel GPU until recently. Actually, our most recent compiler supports OpenMP on our GPU. The part of OpenMP that'll work on it, right? The GPUs can't do everything, but the target directives, some of the simple parallelism, the SIMD directives work for our GPUs in our OpenMP. Other OpenMPs, I think, will emerge that do that for other GPUs. In fact, AMD announced an OpenMP project that they're doing, and there's some things going on for all GPUs with OpenMP. My problem with OpenCL is simple. There's no such thing as performance portability in OpenCL. Now, there's one person on the planet that'll argue with me. His name's Simon McIntosh Smith, Bristol University, and he's wrong, and he'll realize it eventually. Simon and I talk a lot. Simon even wrote a chapter in my last book. My issue is you get performance portability in OpenCL by giving up the features that would drive you to OpenCL in the first place. And I find that an argument, circular argument. Simon hasn't quite come around, and I keep beating on him, and he keeps telling me he's going to prove me wrong, but he hasn't so far as I'm concerned. And the ZIB folks that I mentioned, they've said publicly many times, there's no such thing as performance portability in OpenCL, and they'll rewrite their kernels. So if OpenCL is valuable to you or something like that, just expect to rewrite your kernels. Is that worth it? You know what, if you're going to make another $1 billion on Wall Street because you sped up your financial transaction program, you really don't care about me saying that your code's going to be dead end. You'll take your $1 billion and be very happy. Or if you're going to discover more oil in the oil industry. So there's plenty of customers that can tell me they have the ROI, they'll throw away their code. But if you're writing code that you want to last a decade or two, I think OpenCL is a really bad option, because OpenCL is purposely supposed to be close to the hardware. You're supposed to write close. The charm of it is you write close enough to take advantage of every feature of the hardware, even if an abstract programming model can't. You know, mapping things to texture map memory or this or that. And our challenge with programming models is to try to abstract that so you can write in an abstract level that lasts. OpenCL's goal is not that. OpenCL's goal is to unlock that low-level stuff. So I try to avoid promoting it to the wrong audience, and I think this would be the wrong audience, because I think we're trying to write code that survives longer than that. But if you are trying to write code that takes, you know, that's going to make $1 billion for your company, writing a kernel in OpenCL might be a good way to go, or assembly language or whatever, or anything, CUDA even, you know. No. But yeah, I mean, there's no absolutes here, but I think the goal is getting as much code written in OpenMP or TBB or MPI where it really applies to all platforms, and you make it portable and performance portable is more likely to succeed, in my opinion, than using something like OpenCL.